So we're going to have a hopefully quick video reviewing what should be a complete review topic that you began studying in grade 9, and it is a skill that we're going to rely on very much throughout this unit and throughout the rest of the course. So I'm hoping that we can become a little bit more than familiar with it. I'm hoping we can become masters of it very quickly because we will be relying on it as early as the next lesson. So this is rates of change that we're talking about here. When a function changes at a constant rate, then we would say a graph is linear, right? None of this is new. The rate of change, which we will short form to ROC, the rate of change of a function is the same as the slope of a function's graph. Now we should be masters at calculating slope. Again, you went over this in grade 9. You relied on this in grade 10 and again used it in grade 11. So with slope, the rate of change equals slope. Slope equals, you might know it as rise over run, or that should say delta y over delta x. So let's fix that mistake right away. Delta y over delta x. And that is y2 minus y1 all divided by x2 minus x1. Now, if our rate of change is not constant, then our graph is nonlinear. Okay, nice and easy. If it's constant, it's linear. If it's non-constant, it's nonlinear. Rates of change can be given. They can be calculated or found to be positive, in which case, if it's a positive rate of change, it means our dependent variable, and usually that's y, is increasing. Okay, as our independent variable, that is x, increases. Our rate of change can be negative, and that in that case your dependent variable is decreasing, so it's going down as your independent variable again increases. And if you have a zero rate of change, then your dependent variable is not changing as your independent variable decreases. Now when we see them on a graph, and I know you've seen this before, if you see them on a graph, a positive rate of change will look like this. It's going up as we look from left to right. A negative rate of change will look like this. It's going down as we look from left to right. And a constant rate of change, a zero rate of change, looks like this, where it's not changing as we go from left to right. Now we must always consider when we're stating a rate of change after we calculate it, and in particular when we're working in an application problem, we must always consider the context of the problem and consider our units of measure from both variables. Okay, we will get a little bit of practice going over that in a little bit. So number one, we want to handle here. We're given some data here. This is the amount of gas inside a gas tank as a tank is being filled up. So we want to calculate the average rate of change for various time intervals. So the first time interval is from 0 seconds to 6 seconds. We're going to rely on this equation up here. Our rate of change equals delta y over delta x, and that is it equals y2 minus y1 over x2 minus x1. So from 0 to 6 seconds, our average rate of change equals y2. So we call that 31.2. And rather, let's write the whole thing out here the first time. y2 minus y1 divided by x2 minus x1. Now, in this case, we're working with, let me see here, with time in seconds and volume in liters. So we need 31.2 minus, and here from 0 to 6 seconds, right, minus 0 liters, all divided by 6 minus 0. And that is nice and easy. We can throw that into our calculators here. 31.2 divided by 6, 5.2. And then we need the units. So these units would be whatever was on top, and in this case it was liters, right? So we had 31.2 liters minus 0 liters. 6 seconds on the bottom divided by 0 seconds. So our final units are liters divided by seconds. Liters per second, we say. Now moving on to the average rate of change from 3 to 6 seconds. Nice and easy. We're following the same formula. Our average rate of change, we can write it a different way this time. Delta y over delta x equals 31.2 liters minus 15.6 liters. Nice and straightforward. All divided by 6 seconds minus 3 seconds. And this brings us here, once we throw that into our calculator, we should find it again equals 5.2 liters per second. Now I want you to go on and calculate that from 5 to 6 seconds. You can pause the video here and find that. You should find that our average rate of change equals, again, 5.2 liters per second. So since our average rates of change are equal or are constant, then we say the graph is linear. Fantastic. Now I know this is really straightforward. That's part of it. I promise you it will get more challenging as we move forward. Maybe not so much in this lesson, but definitely in the next lesson we'll be bringing forth some new ideas. Now here, so example 2. Here we have a table and a graph representing Usain Bolt sprinting in a race, okay, where our distance is in meters, our time is in seconds. Here we want to calculate our average rate of change for 3 different intervals. First, from the first second till the second second, then the third till the fourth, and the fifth until the sixth. I want you to take a look here at the graph first before we calculate these and try and predict which rate of change will be the greatest and which average rate of change will be the least. Okay, you should be able to handle something like this on your own. But we will go through at least the first one together here. So from 1 second to 2 seconds, we're working right in here, and that is with these data points. So again, our average rate of change equals, in this case, we're handling 14 minus 6. Both of those are in meters, divided by 2 minus 1. And that is 14 minus 6, that's 8, divided by 2 minus 1, that's 1. So 8 meters per second. Here, this is, you'll notice meters per second. You might recognize that, in particular if you've taken a physics class before. That's a speed, right? Our rate of change here is how quickly our distance is changing over time. In other words, our speed, or Usain Bolt's speed, that is. Next, we'll go into, let's give ourselves another color here, from 3 to 4 seconds. So from 3 to 4 seconds, our average rate of change equals 38 meters minus 24 meters, all divided by 4 minus 3. Nice and easy. Here we have 14 meters per second. So we're seeing a different rate of change. And again, this is right here from 3 to 4 seconds. And lastly, we have from 5 to 6 seconds an average rate of change. We should, again, this should be pretty straightforward for you. You know what, I'll leave that for you to finish. But we should find it equal to 12 meters per second. Now, we need to ask ourselves, is our average rate of change constant as time increases? Well, we just took a look at 3 different time intervals. All of them we calculated to be different rates of change, and that tells us, no, it's not constant. And if it's not constant, that means that we have a non-linear relation. And that makes sense. If we look at our graph up here, it does not look linear in the slightest. It looks like that rate of change is frequently changing. Now, what else is revealed from our average rates of change from this interval? Well, we can see that Usain Bolt was fastest of these 3 intervals, was fastest between the 3rd and 4th second. B/W, that means between seconds 3 and 4. Awesome. Now we are going to leave this example behind, and we'll go into a little bit more detail. So we can start using, again, when we're calculating our rate of change, our average rate of change, we can start using function notation because we're masters of function notation at this point. So if our function is f at x, and it's changing over an interval from x1 to x2, then we can calculate our average rate of change as f at x2 minus f at x1, all divided by x2 minus x1. And that is just another fancy way of writing what we wrote up top, and that is y2 minus y1 divided by x2 minus x1. Now, this average rate of change, again, when we put it towards a graph, an average rate of change is the slope of the line, is a slope of a line, right? Now, a line that joins 2 points on a curve, now we're heading away from a linear function, on a curve is called a secant, and I believe you have heard that term before. In this case, our secant is in black. The average rate of change between 2 points, so the 2 points that the secant is crossing on a curve, the average rate of change is given by the slope of that secant. Now again, you can find that slope of the secant using the exact same strategy that we have been using. Okay, so if we look at another application, we have a coffee shop. Their profit is given by this equation here. There is an error in this equation. I'm sorry for so many errors this time. That is, it should be negative 625c squared plus 5,000c plus 1,000, where our profit as a function of cost, that's P of C, is the profit in dollars, and C is the number of cups sold in thousands. So let's try and find the average rate of change for profit during these intervals. Now this time you'll notice we're not given a table of values. We're not given a graph. We need to evaluate this function at certain positions, at given C values, in order to find our average rate of change. So our average rate of change between 3 and 4 seconds is P at C, which is P at 4 minus P at 3, all divided by 4 minus 3. Okay, and that is, we're using this function notation here. You'll notice our x values rather than x. In this particular example, our independent variable is C, the number of cups sold in thousands. Now we can then evaluate this. So that means we need to evaluate here P at 4. Right? If we're going to work forward here, we need to evaluate P at 4, and that means we're substituting C equals 4 into this entire equation. So that is negative 625 times 4 squared plus 5,000 times 4 plus 1,000. Okay, so that's our P at 4. Then we need to calculate P at 3. Okay, well that's negative 625 times 3 squared plus 5,000 times 3 plus 1,000. And we can put this into our calculator, and I know it's nice and long. We might have to do it in a few steps, and that's okay. But all of this will be divided by 4 minus 3, and that just equals 1. So we can actually, at this stage, we can remove that denominator. Now what we should find is P at 4 equals 11,000, and P at 3 over here equals 10,375. So that is our, and let's give ourselves, there we are, we can squeeze it in here. That is 625, and here are units. Our units are cups in thousands. Cups of coffee sold in thousands divided by dollars. So 625,000 cups, per dollar. And that should be the other way around here. I'll leave that in because we all make mistakes. So it should be dollars, which makes sense. It's a price per. So dollars per 1,000 cups. And that is, this is a positive number, so that means our profit is increasing as we go from 3,000 cups sold to 4,000 cups sold. Now what I want you to do, and I know I have not left you a whole lot of space, I apologize for that. I want you to handle number 2 right here. Now this time we do not need to necessarily take up as much space. We could just we go for our average rate of change. I trust that you are following what we're doing right here. And what we need to do here is we're evaluating P at 5 this time minus P at 4, all divided by 5 minus 4. Okay, and into this calculator, we can find P at 5. We're doing that the same way we did before, and P at 4, same thing. You should be able to handle something like this. The answers will be up on the board in a moment. And here we are. So we can see as, let me remove these symbols. Perfect. So our average rate of change should be negative this time, $625 per 1,000 cups. And that's from 4 to 5 seconds. And from 5 to 6 seconds, our average rate of change should be negative $1,875 per 1,000 cups. Now, if we stop and think about this as we move forward from 3,000 cups to 6,000 cups, should it make sense that our average rate of change, that is our slope of a secant, goes from increasing to decreasing by that same amount and then decreasing by even further? Well, the general shape, the general function that we're working with here appears to be some kind of a quadratic function with a negative a value. So if it has as we see right here, if it has a negative a value, it opens down. That makes sense. There's a maximum at some point in there, and from 5 until 6 seconds is probably further along on a curve. So this makes sense. So as more cups of coffee are sold, then the profit decreases. Now our average rate of change goes from, sorry about this folks, goes from positive to negative between the intervals 3 and 4 and 4 and 5. What does this suggest? This suggests that we have a vertex, a maximum point, at some point between 3 and 5. And because it goes from positive to negative, but they have the same values, so positive 625, negative 625, even further, it suggests that there is a maximum profit at 4,000 cups. Good. So this, I'm hoping this in particular gave us more practice, and I'm hoping a little bit more comfort, always ensuring we're using our units as we come into any concluding statements with rates of change. And I'm hoping we're feeling a little bit more comfortable calculating an average rate of change. You should now be able to handle all of the practice work for 2.1.